We talked about seasons and days and energy transfer. Now we're going to go into the specifics of the days. We're going to look at radiant absorption, and we're going to look at conduction and convection, and then radiant emission all day long and all night long. Let's get into it. This graph here shows two sections. The first section has a daily temperature line with a minimum and maximum from midnight to midnight. And the bottom part of the graph shows radiant energy. Radiant energy being emitted, that's the red line, and radiant energy being absorbed during the day, that's the orange line. We're going to learn how to work with them together. We're going to start at sunrise. And sunrise, you note here, is down at 6 a.m. And you might be noting that there's two troughs here. There's a trough for the minimum temperature, and there's a trough for the minimum outgoing energy from the earth, the minimum emissions. And those two things seem to go together, because when we have minimum emissions, we're having very little energy move off the earth, and we have no solar absorption during that time because the sun's been down all night. So it makes sense that we would have a minimum temperature at that time at sunrise. It seems counterintuitive because people think of the minimum temperature being sometime around midnight, but it's actually at sunrise. We can look at this temperature in a different way. We can look at this temperature by altitude. So now we have three different graphs looking at what's happening at sunrise. The highlighted area in this graph looks at the 5 a.m. temperature from the surface level at a 0-foot altitude up to about 8 feet of altitude over the course of 5 a.m. And it looks at it versus temperature on the x-axis. So what we're noting here is that at sunrise, the temperature of the surface right around the grass is really cool. All the emissions all night long have cooled that surface temperature. Those emissions went up and emitted out to the first few inches, and there was conduction over the first few inches as well. And a parcel of warm air from those first few inches was convected up, and that convected up parcel actually ended up warming the area above the ground. Very different. When you think of altitude and temperature, you think of the temperature decreasing as you go up in altitude. But overnight, those emissions have resulted in a parcel that warms the area, that lifts and convects and warms the area above. That's called a radiant inversion. So normally we would see temperature drop over altitude. That pattern is inverted by a radiation emission called a radiation inversion. At noon, things are different. At noon, we're right around here, and we notice that there's a peak in solar absorption on the red line. And we notice that the orange line has a peak in solar absorption. The red line is gaining in emissions, and the temperature line is gaining in temperature for the day. The temperature for the day does not peak at peak solar absorption because, again, we've got that average thing happening, so there's a lag there. But the temperature is rising. If we look at our temperature over altitude, things have changed quite a bit. Look at the highlighted area now. We've got a temperature at noon that is the line that is this yellow line here. And this temperature at noon at the surface has skyrocketed with the peaking absorption that's at the surface. And the temperature at the surface is at about 43 degrees Celsius, somewhere around 110 degrees Fahrenheit. It's moved about 50 degrees Fahrenheit in 7 hours due to that absorption and that radiant energy in. We normally record temperature at the altitude, at that 5-foot altitude up here. We record it through a weather station, and we recorded at that just to avoid those big extremes at the surface level. Things are a lot different at 5 feet. And what you're noticing there is that this 5-foot level is a lot more moderate. It is looking at the convected parcel that has come up from the surface. That surface has emitted, that surface has conducted, it's sent out a parcel, the parcel has moved up into the atmosphere, and now we see that same decline that we're used to, that the temperature drops as the altitude climbs. And the reason that we're noting that at noon, and you follow this line up, we're noting that at noon, is there's no way you could sustain that high 110 degree Fahrenheit temperature when it moves up in altitude. So you're seeing that the temperature at altitude, even at 5 feet, is just a bit lower. At 4 p.m., let's move out to here. At 4 p.m., something really interesting happens. The curve for incoming solar absorption meets the curve for outgoing solar emission. And at this point right here, you'll notice that it's maximum temperature for the day. In other words, you've accumulated so much absorption that you are at a place now where you are meeting the emission. And let's take a look at what happens at 5.5 feet up. You may say to yourself, wait a second, we were at 110 degrees Fahrenheit at the surface at noontime. How can you possibly get a maximum temperature at 4 p.m. when you were at 110 degrees at noontime at the surface? We report the maximum temperature for the day not at the surface. We report it at 5.5 feet up at the weather station here. And the reason we do that is just to avoid those big extremes at the surface. So what you see here is at the dark orange line, which is the 3 p.m. line. Follow that down. And you've got this line at dark orange noted at 3 p.m. At 3 p.m., you've already got a lot of emissions going on, and those emissions have taken the surface temperature down from that 110 degrees at noontime down to about 100 degrees. You've got a lot of energy moving off and being emitted and conducting off and sending out a parcel that is convecting upward, so that by 3 to 4 p.m. at the station height, you've got your highest temperature of the day, your maximum temperature of the day. And that is one thing that I would record at about 87 degrees there, at about 32 degrees Celsius, your maximum temperature of the day. A lot of that is due to the efficiency of that forced convection that's coming out from the potent emissions and coming out from the conduction, warming that parcel and sending that up. There's also forced convection because the atmosphere starts to turn over in the afternoon with this dramatic difference of warm and cool. It starts to send in winds that move that convection up, and you're seeing it in that altitude difference. So in general, daytime warming near the surface and this warming that you see that's very dramatic here at the surface tends to cool at station altitude and at the rest of the altitudes that you've noticed. Now, let's look at what's going on overnight. I have here a midnight view here where you've got a declining emission curve. So these emissions peaked right around 4 p.m. and now they're trailing off, and no solar energy at all in this area. And you've got a temperature that's really falling rapidly at the midnight area. See how this looks on our altitude sounding. So the line that we're following now is the 9 p.m. line, which is the pink dashed line here. And if you look at that pink dashed line, it should remind you of the 5 a.m. line that was a radiation inversion. Yes, it's going, that temperature is increasing over altitude. That surface temperature is lower at 9 p.m. and the temperature at the weather station is higher at 9 p.m. You've got a radiation inversion here. Why do you have that? You have that here because there is no conduction happening in this area because you haven't got any more solar absorption coming in overnight. All you've got is the overnight emissions, the radiant emissions that are warming the parcel that is above the surface. When you've got that parcel that is above the surface, that parcel is warming up and then it's slowly convecting up to this area to warm this area by the weather station. So again, you've got another radiation inversion overnight. In general, overnight, you'll note nighttime cooling near the surface, and you'll note nighttime warming at altitude for radiation inversions. Strong radiation inversions really happen with cold air at the surface and warm air above. The ideal conditions for this are windless nights that don't have a lot of convection, long winter nights, clear skies, dry air. Range of temperature from surface to 5 feet at these weather stations. Let's look at the range of temperature. If we look at and compare peak times at the surface, you would say peak times at the surface happened at noontime. The orange line here at 110 degrees Fahrenheit, 43 degrees Celsius. We would subtract that from the lowest temperatures at the surface. Those lowest temperatures of the surface happened at dawn. We were right around 11 degrees Celsius there. We've got a broad range of temperature daily of about 32 degrees Celsius between highest temperature and lowest temperature at dawn. Wide range there. If we look at the standard level at the weather station, we would be looking at highest temperatures that didn't happen at noontime, but that had happened at 3 p.m. That was at about 30 degrees Celsius at 3 p.m. And you're subtracting that from the dawn temperature, which was at about 18 degrees Celsius. 12 degrees Celsius for a range of temperature at 5 feet, much less than the range at the actual surface. And that correlates to what we see at skyscrapers. For instance, if we compare the range of temperature of the surface to 1,000 feet up, you would note that at the surface, you had a range of temperature that might range between 21 degrees Celsius and 13 degrees Celsius overnight, an 8-degree change of temperature. But up at the top of that skyscraper, you get much less of a range of temperature because the surface heating really drives that difference. The range of temperature is greatest at the surface. That's it for that.